So we're going to study exergy in this chapter. What does that word look like? Looks like another word, energy. There's one letter difference between energy and exergy. It's X versus N, true? So if you were asked to give a definition of energy, most people would say something like, well, it's ability to do work. Guess what? That's a great definition for exergy. The ability to do work. Energy is the ability to have an effect. Make something hot, make something cold, maybe do work as well. But energy is a broader concept. And it's the ability to have an effect, okay? But exergy is the ability to have an effect of work. So as an engineer, you know that sometimes your ability to do something useful is destroyed or diminished because of irreversibilities, friction. Is energy ever destroyed? Energy is conserved. But its capacity to do something that you desire, like work, can be destroyed because of or diminished because of irreversibility. So that's the concept of exergy. We'll talk about exergy as a property. We'll talk about having an exergy balance for closed systems, just like we did for energy. Exergy balance for open systems, just like we did for energy. And then we'll talk about a new form of efficiency description for turbines, compressors, pumps, heat exchangers. Just like we had isentropic efficiency, now we'll have what they call exergetic efficiency, sometimes also known as second law efficiency, because it combines energy and entropy concepts into one new property called exergy. So exergy is defined as the maximum theoretical work, meaning you're not really going to get that work out of it, but it's plausible or hypothetical that it could be attained under special conditions, where it's defined for a system as the system undergoes a theoretical process and comes into equilibrium with some local environment. So often when you have a heat engine, if you have a high temperature source and a low temperature sink in which you can throw some energy away, you can develop some useful work by taking some part of QH and converting it into W, but some has to be thrown away, true? That's a restriction, second law. So what happens is we're going to study systems that may start hot and high pressure, and as they undergo a process, they'll become cooler, equal temperature with the ambient environment, as well as lower pressure, equal pressure with the ambient environment, or so that you get the maximum amount of work out of the system during that hypothetical process. So exergy is a property of the system. It depends on not only the properties of the system itself, but also the properties of the environment. So you think about this system here. Maybe it starts out high temperature, high pressure. It's surrounded by an environment. That environment's at a lower temperature and a lower pressure. I know it doesn't always have to be higher, lower. You could start out with a really cold system in a state of vacuum. But most of the time, it's a hot system under high pressure. And as that system undergoes a process, that temperature goes to T naught and P goes to P naught. So it comes into thermal equilibrium and mechanical equilibrium with the environment. And the maximum amount of work theoretically obtainable from that system during the process is called the exergy. So the exergy depends on the temperature and pressure that you start at, as well as the environment temperature and pressure. What does that subscript look like on that T and that P? It's 0. 0. Not the letter O, but the number 0. Dead state. When the system is in equilibrium with the environment, it's not capable of producing any useful work. It's done. So it's said to be dead. It's at the dead state. Does it still have energy? Well, yeah. Does it still, but that energy can't be converted into useful work, so it's dead. So the dead state pressure is often 1 atm or 100 kilopascal. That's a typical value for the dead state pressure. As likewise, 225 degrees C is the dead state temperature. So at thermal equilibrium, the system temperature is equal to the environment temperature, and the mechanical equilibrium, the system pressure is equal to the environment pressure. Now, let's just get to the bottom line here. We have some equations that we are already familiar with in terms of energy. This equation right here, E, specific energy, is equal to U plus KE plus PE. Does that equation look familiar? All right, what does the KE stand for? Kinetic energy on a per unit mass basis, it's 1/2 V squared. What's PE stand for? Potential energy. It's GZ, potential energy. So U is the internal energy. When you sum them all up in the engineering thermodynamics that we study, those are the three forms of energy that we have for our system: internal, kinetic, and potential. This one deals with its speed, V. This one deals with the elevation, U. And primarily, you can think of internal energy as how hot it is, as well as how high pressure it is. If it's under high pressure, high temperature, well, you have a lot of internal energy. Okay. So E is that total energy. For a closed system, we use it a lot. Now, the next slide will derive this equation. It's the Exergy for a closed system. Let's compare. What is similar about those symbols? What's different about those symbols? Nothing. It's E is E. So guess what? You got to pay attention to the context. A lot of times I'll write EX or something, but to try and say this is Exergy. But it's not often I do that. In a previous edition of this textbook, they used a symbol like this, psi, for availability, or A for availability, or some other. They tried to use a different font for Exergy, but it was so confusing. I think this version in the last couple editions of this textbook, they just said, we give up. E is for energy, E is for Exergy. You have to pay attention. All right? Okay. Now, what is U? Is that the same U? Yes. All right. What is this V right here? Specific volume. Specific volume. So if I said, give me the specific volume of water at a temperature of 300 degrees C and a pressure of 200 kilopascal, do you think you could go and get that specific volume? Sure could. Oh, it may be superheated water. It may be subcooled liquid. It may be two-phase something, but two independent properties fix the state. I was able to get U and V. And what about S? What is S? Entropy. So this is a really different type of property. Exergy depends on U, V, and S of the system in its current state. But it also depends on P naught. What is P naught? Ambient environment pressure, typically around 100 kilopascal. What is T naught? Environment temperature. Now, because we're going to be multiplying T naught times S, what do you think? Should I put in 25 degrees C for that T naught, or should I put in a different value? I better put in the absolute temperature. I better put it in. So it'd be like putting in 298 Kelvin. Warning, warning, warning. Don't just throw away units and just hope it all works out, or expect Manteuffel to give you a lot of partial credit because you ignored units. No, 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 no. Engineers, you got to get it right, right? You got to get it right. So you got to know where the pitfalls are. The pitfall is when you need to put in temperature and absolute scale and you put it in a relative scale, wrong. Okay? And you lose a lot of points. It needs to be very painful. How many people remember the first time they ran out of gas? Oh yeah, it was so painful to me, so painful. I look at that gas gauge all the time now. What are you doing, looking at the gas gauge again? Yeah, keep your eyes on the road. I'm going to see if I'm going to run out of gas. It was such a painful experience. That's why in engineering we make it such a painful experience. You mess up the calculations in some small way. Professor, I got the concept. I know, but the concept isn't that hard anyway. You've got to get the right answer as well. So don't mess up the units, please. That's me pleading with you. Pay attention to your units. Now, what about S naught, V naught, and U naught? Where do you think? That's the internal energy, the volume, and the entropy of my substance of interest, of my system, when it gets into the dead state. It may never get to the dead state, but I need to be able to evaluate U naught, V naught, and S naught, meaning I need to be able to evaluate, just like here, I need to evaluate the specific volume of water. Oh, that was my substance. Not at 300 degrees C, but 25 degrees C. Not a pressure of 200 kilopascal, but 100 kilopascal. See that? That's what V naught is. My same substance evaluated at the dead state condition of T naught and P naught. Now, what do you think I have under the black box? These are all for closed systems. What do you think I have under the black box? Open systems. That's exactly right. So what we do is we uncover and we see, does anybody remember the property enthalpy? And do you remember, like, hey, why do we have a new property, enthalpy? I don't understand why it's there. Remember that when you were in Thermo 1? Like, oh, yeah, enthalpy. It's a new property. It's a combination of U plus PV. What does the PV term represent? Flow work, pushing it in and out of the pipe that goes into and out of the control volume. It's a flow work contribution. So we lumped it in with the internal energy. We call that enthalpy. Well, guess what they do with Exergy? They have another Exergy. Just like this was an energy for the closed system, this is an energy called enthalpy for the flowing in and out. You will have, guess what, a different type of Exergy. It will be what type of Exergy? Hey, we're not that original. We're just engineers. Flow Exergy. Okay? And so the flow Exergy is for open systems. This textbook adds a subscript F right there. You say to yourself, why didn't they put use of F and then call that U plus PV? I don't know. That would have probably been good for parallelism, you know. But they called it enthalpy. And so when we talk about Exergy, you'll have the Exergy property evaluated for closed system problems, and then you'll have the flow Exergy, E sub F, for open system. Actually, for the open system flowing, it's a little simpler. Can you see that in the formula? But they also lump in the kinetic and the potential energy term there. Okay. All right. Let's do the derivation. So let's do the derivation for the Exergy of a closed system. Here it is written out not on a per unit mass basis, but on a total mass of the system basis, right? Cap U minus U naught, etc. All right. What are the SI units for cap E Exergy as shown? What are the SI, traditional SI units for this property? What are the units? Kilojoules. Right, right. That's why I like the second version of this. You can get alphanumeric input. I think you'll be able to put K and J. Right? Okay, correct answer. Instead of giving you option A, B, C, and D. Right? Okay. Now, so what we do is we introduce the system, shown in blue, at the temperature T and P. Think about hot, high-pressure system. It doesn't have to be, but think about it that way. Put the environment, purple. Is the environment everything else in the universe? No, it's not. The system with its local environment plus everything else in the universe is the universe. But there's stuff outside of the system and outside of the local environment for that system. All right. We're interested in having that system that's blue undergo a process where it becomes into thermal and mechanical equilibrium with the local environment, which is purple. And by doing so, WC, the work out of the combined system, that's the C subscript on there, out of the combined system can raise a weight in a gravitational field. That's our exergy. It's doing useful work. Okay. So what do? You write the energy balance for the combined system. Does that look good for an energy balance of combined system? What is that E there? Is that energy or exergy? Energy. Energy, that's right. And so Q sub C, they're showing you that there's really no more heat transfer from the combined system, the outer edges of the environment, with the rest of the world. So that's zero. But what about WC? That's the term we're interested in computing. We're interested in computing WC and maximizing it. All right, so we can rewrite the first law for a combined system as WC, what we were interested in computing, equal to the minus the change in the energy of the combined system. Well, the change in the energy combined system can be the sum of the energy of the system and the change in the energy of the environment. Does that equation look good? Don't worry, you're going to get lost in a minute, if you're not all lost already. Good thing is this derivation's in the textbook. All right, now I expand out the terms going from here to there and here to there, true? So what does it show? Well, the change in the energy of systems, the change in internal plus a change in kinetic plus a change in potential of the system, and likewise for the environment. But for the environment, does it have any change in kinetic energy? No, the environment's just a big old lump of hot or cool surroundings. Just think of that as outside air. All right, so no change in KE or PE for the environment. Then you rewrite this, just combining a little bit. You have that the change in the energy of the combined system is U naught minus U minus KE of the system minus PE of the system plus the change in the internal energy of the environment. Because this delta U, it's U final minus U initial. It starts at the current system, undergoes a process so that the system is now in thermal mechanical equilibrium. So U2 is equal to U naught, right there. That's U2 is equal to U naught. Okay. Now follow this little path. Go this way. All right. Now let's apply the first law only for the environment. So you have the change in internal energy of the environment equal to the integral of del Q. That's the heat transfer from the system into the environment. Remember, there is no heat transfer from the environment to anywhere else. Minus the integral del W of the environment. And notice that we're not interested, the environment doesn't expand either. So this work is only from the system to the environment. Or as shown in this energy balance for the environment, it's from the environment to the system. Notice that you can rewrite this from the environment as negative. What is the heat transfer from or to the system? So you're changing perspectives. Am I talking about heat transfer Q for the environment or heat transfer for the system? They're related by being the opposite sign of each other. And the change in the work for the environment is just pushing back the environment. And the environment's at P naught, so that's an easy integral PdV. It's P naught times V naught minus V. All right, which you then can change for this V of the environment to the V of the system with the negative sign. So now we have the change in internal energy of the environment is equal to the negative of the integral del Q plus P naught. This is what they call a non-useful boundary work expansion term. pushing back the environment doesn't help you raise a weight in a gravitational field. Go to the second law for the environment. Now we can see how to get the integral del Q and replace it right here, so that we have the change in internal energy of the environment equal to, it doesn't look pretty, does it? But there it is. It's a combination of the first law and second law. At this point, I'll scroll down a little bit, and you take the result here and the result there, and you combine them. And so you get that the change in the energy of the combined system is as shown. Do the second law for the entire system. Multiply that by T naught. Take that equation, combine it with that equation, and you're almost there. You have an expression for the change in the energy of the combined system. You see something like T naught sigma over here and a bunch of other terms. And then you look and you say, you know what? The maximum work out of the combined system, it's only going to be maximum when sigma is equal to what? See, there's a negative sign right there. Sigma is always positive. You can never have entropy destruction. You only have entropy generation, true? Due to irreversibility. Sigma is positive. It can't be, if it's 0, it's completely irreversible. It can never be negative. That's from Thermo 1. So guess what? The best you can do is when sigma is equal to 0. That makes this a maximum. And it's equal to, by name calling, a change in a new property called, well, it's a change in the energy of the system. It's this. So what you do is that term drops out and you're left with this term plus kinetic and potential energy that the system starts with. And you define the exergy of the system as that, the maximum useful work. So the maximum useful work out of the combined system is the exergy of the system. You like that? It's in the textbook as well. I tried to do it this way. Let's solve a problem. A system has 3 kilograms of water initially at 120 degrees C and a quality of 95%. And it fills a piston cylinder assembly. This is typo, 95% quality. The water is heated, showing a flame here, heating it, until the temperature of the water rises to 125 degrees C. Determine the change in volume of the water. What are they asking us to calculate for part A? V2 minus V1. What would be the units on that answer? Meters cubed. Notice, let's just go through. What are they asking us to calculate for part B? The change in the energy of the water. It would be E2 minus E1 in units of kilojoule, but you notice that there's no macroscopic velocity of this water. There's no change in the elevation of this water. Hence, it's just U2 minus U1. The change in the energy is limited to the change in the internal energy of the water. What about the change in the entropy of the water? What are they asking us to calculate? S2 minus S1. What are the SI units for the answer to part C? Kilojoules per Kelvin, because we already have the 3 kilograms. And then what about the last, part D? What is the change in the exergy? What symbol do we want to use for exergy? We used V for volume, U for internal energy, S for entropy, E for exergy. So it's E2 minus E1. Is there anything different between what I wrote here and right there? No. It's just the interpretation is energy, and now it's exergy. What are the units on the change in the exergy? Kilojoule. Kilojoule. So let's go ahead and do this. How do I solve for part A? I want to get V2 minus V1. How do I do that? The mass times the specific volume 2 minus specific volume 1. This one I already know is 3 kilograms. Then I'm left with the challenge. Can I get the specific volume of water, H2O, whoops, let me write it this way. The specific volume of water at state 1, which is 120 degrees C and 95% quality. Can I do that? Could you do that? And then I just need to now find V2, which is, I'm still water, but I need 2 properties to fix the state so I can get the specific volume of water. Okay? What happens when I heat it? These represent weights of the piston, right? Does this go up a little bit? Do you think it expands a little bit? Yes. Yeah. All right. So, help me a little bit. How do I fix state 2 so I can get the specific volume at state 2? Okay, it's 125 degrees C. That's one of the properties that I need. And the other property is? Pressure is it. Very good. You learn something. No matter what they say. Your parents are probably, so upset at you because you come home and they say, what class did you pass last? Oh, I passed thermodynamics. What did you learn? Nothing. Right? Right? No, you can say, I learned a lot. So this is the pressure, which is the saturation pressure, PSAT. I can't write today. Saturation pressure at 120 degrees C, right?
125 degrees Celsius, shouldn't it be 25?
This is the dead state temperature, and we'll only use that for the very last problem, part E. D, only part D, right? So it starts at 120 and goes to 125 degrees C by heating it. All right. Now, what about U2? Let's stay here. U2 minus U1. Is that M times U2 minus U1 the specific internal energies?
Yes.
And isn't it the same type of game? Right? That's right. Same process. Okay, instead of getting V's, get U's. How about S2 minus S1 for part C, the change in the entropy of the water?
Mass times little s2 little s1.
Does that look good? Can you solve that? Now the last one, part D. What is the change in the exergy? Is it lowercase m times E2 minus E1? Oh, I forgot what that formula is for the exergy. E is equal to U minus U naught plus P naught V minus V naught minus T naught S minus S naught plus KE plus PE. Now, both of those terms are negligible because we don't have any macroscopic kinetic potential energy, right? So now I just have to write that for state 1, and then rewrite it E sub 2, U2 minus U naught, plus P naught, V2 minus V naught, minus T naught, S2 minus S naught. Take the difference, and I get something like U2 minus U1 plus P naught V2 minus V1 minus T naught S2 minus S1. Do you think so?
Yes.
So even though that property exergy is scary with all these U naughts and V naughts and S naughts, sometimes you don't even need to calculate them. You just need to get the change in U, P naught, change in V, T naught, change in S to calculate the change in the exergy. Would you like numeric values for some of these answers so you can check them later? So for the change in the volume, I calculated it to be 0.172 meter cubed. Notice I use a box in units. All right? And then the change in the internal energy, 329 kilojoules. Change in the entropy, 0.922 kilojoules per Kelvin. And the change in the exergy to be 71.0 kilojoules. Please solve a problem like this, okay? Make sure you can do that. I'm going to go ahead and stop. Thank you for your attention.